What if everything you thought you knew about the beginning of the universe was just the tip of the iceberg? Picture this, a moment before time itself existed, a state so mysterious that even the brightest minds in science can only speculate about it. What came before the Big Bang? It's a question that challenges not just our understanding of the cosmos, but the very nature of existence. Today, we're diving into the mind-blowing theories that attempt to unravel this cosmic mystery. From endless cycles of universes to higher dimensions and even the possibility of a multiverse, we'll explore the ideas that push the boundaries of what we think is possible. By the end of this video, you'll walk away with a new perspective on the universe, and maybe even a few answers to questions you didn't know you had. So, are you ready to step beyond the Big Bang and into the unknown? Let's begin. Now, let's take a step back and revisit the cornerstone of modern cosmology, the Big Bang Theory. This groundbreaking idea tells us that around 13.8 billion years ago, the universe as we know it began from an incredibly hot, dense state. In a fraction of a second, it expanded rapidly, cooling and forming the building blocks of everything we see today: stars, galaxies, and even the fabric of space and time itself. But here's the thing, the Big Bang isn't just about the birth of the universe. It's also the starting point for asking one of the most profound questions in science: what came before? Without this theory, we wouldn't have the framework to explore the mysteries of existence. It's like a cosmic map, guiding us to the edge of what we know and pointing us toward the unknown. So, as we dive deeper into the theories that attempt to explain what might have preceded the Big Bang, remember this: every idea we explore builds on the foundation laid by this monumental discovery. And that's what makes it so essential to our understanding of the cosmos. Now, let's shift our focus to a question that challenges not just science, but the very way we think about existence. What does before even mean when we're talking about the Big Bang? Here's the twist: time, as we understand it, began with the Big Bang. So, asking what came before is like trying to find a place north of the North Pole. It's a concept that doesn't quite fit into our usual framework of cause and effect. This is where things get mind-bending. If time didn't exist before the Big Bang, then the idea of a before might not make sense at all. Yet our brains are wired to think in terms of beginnings and endings, causes and consequences. This is why the question of what came before the Big Bang pushes the boundaries of human understanding. It forces us to rethink not just the universe, but the very nature of time itself. Scientists and philosophers alike grapple with this puzzle, trying to find ways to describe a state of existence or non-existence that lies beyond the limits of our current knowledge. It's a reminder that sometimes the most profound questions don't have easy answers, but they inspire us to explore the unknown in ways we never thought possible. Now, let's take a step into one of the most fascinating ideas that attempts to answer the question of what came before the Big Bang: the Cyclic Universe Theory. Unlike the traditional view of the Big Bang as a singular starting point, this theory suggests that our universe is part of an endless cycle of expansion and contraction. Imagine the universe as a cosmic heartbeat, expanding outward in a Big Bang, then eventually collapsing back in on itself, only to explode again in a new Big Bang. This cycle repeats indefinitely, meaning the Big Bang isn't the beginning of everything. It's just one moment in an infinite series of cosmic rebirths. The scientific basis for this theory comes from combining insights from general relativity and quantum mechanics. One of the key proponents of this idea is physicist Paul Steinhardt, who, along with Neil Turok, developed a model called the ekpyrotic universe. In this model, the Big Bang is the result of a collision between two higher dimensional objects called branes. These collisions trigger the expansion of our universe, but the process doesn't end there. Over unimaginably long timescales, the universe cools, slows, and eventually contracts, setting the stage for another collision and another Big Bang. This theory also ties into the concept of entropy, the measure of disorder in a system. In a cyclic universe, entropy doesn't build up endlessly with each cycle. Instead, it's reset during the contraction phase, allowing the universe to start fresh each time. This idea helps address some of the challenges posed by the traditional Big Bang model, such as the question of what caused the initial explosion or what existed before it. While the cyclic universe theory offers a compelling alternative to the idea of a single Big Bang, it's not without its challenges. For one, it requires the existence of higher dimensions and brains, which are still speculative concepts. Additionally, the mechanisms that would allow entropy to reset during each cycle are not yet fully understood. Still, the cyclic universe theory opens up a new way of thinking about the cosmos, one where beginnings and endings are part of a grand, eternal rhythm. And as we continue to explore this idea, it reminds us that the universe might be far more dynamic and interconnected than we ever imagined. Now, let's take a closer look at the evidence that supports the cyclic universe theory and the challenges it still faces. One of the key pieces of evidence comes from the cosmic microwave background, or CMB, which is the faint glow of radiation left over from the early universe. Scientists have found subtle patterns in the CMB that some argue could be remnants of a previous cosmic cycle. These patterns, known as temperature fluctuations, might hold clues about the universe's history before the Big Bang. For instance, certain anomalies in the CMB, like large-scale cold spots, could potentially be explained by the cyclic model, suggesting that our universe might have inherited features from a previous cycle. However, not everyone is convinced. Critics of the cyclic universe theory point out that the evidence from the CMB is still open to interpretation. While the patterns might align with the cyclic model, they could also be explained by other theories, such as inflation, which describes a rapid expansion of the universe immediately after the Big Bang. This leaves the cyclic model in a tricky position. It offers a compelling explanation, but it's not the only one on the table. Another challenge for the cyclic universe theory is the question of how entropy, or the universe's tendency toward disorder, is reset with each cycle. In the traditional view, entropy only increases over time, leading to the eventual heat death of the universe. But in a cyclic model, entropy would need to decrease during the contraction phase to allow the universe to start fresh. While some physicists propose mechanisms for this, such as quantum effects or interactions between brains, these ideas are still largely speculative and lack experimental confirmation. There's also the issue of higher dimensions and brains, which are central to the cyclic model but remain unproven. These concepts come from string theory, a framework that attempts to unify all the forces of nature. While string theory is mathematically elegant, it has yet to produce testable predictions that could confirm the existence of these extra dimensions or brains. Without such evidence, the cyclic universe theory remains an intriguing but unverified possibility. Despite these challenges, the cyclic model continues to inspire researchers because it offers a way to think about the universe that avoids the idea of a singular beginning. It suggests that the cosmos might be far more dynamic and interconnected than we've ever imagined, with each Big Bang being just one chapter in an endless cosmic story. As scientists continue to explore this idea, they're not only pushing the boundaries of our understanding, but also reminding us that the universe is full of mysteries waiting to be unraveled. Next, we'll explore another mind-bending theory, the multiverse, and how it attempts to explain what might have existed before the Big Bang. Now, let's shift our focus to another fascinating idea that challenges our understanding of the cosmos, the multiverse theory. Imagine for a moment that our universe is just one of countless others, each with its own unique set of physical laws and properties. In this view, the Big Bang wasn't the beginning of everything but rather a local event within a much larger, perhaps infinite, cosmic landscape. This theory opens up a mind-bending possibility. What we call the Big Bang might simply be one of many such events happening across an unimaginably vast multiverse. The multiverse theory attempts to address the question of what came before the Big Bang by suggesting that there was no single before. Instead, there could be an endless array of universes, each with its own timeline and history. Some of these universes might have existed long before ours, while others could be just beginning. In this scenario, the concept of before becomes relative, tied to the specific universe you're observing rather than a universal starting point. One of the most compelling aspects of the multiverse theory is how it ties into other scientific ideas, such as inflation. According to the inflationary model, the early universe underwent a rapid expansion, stretching space itself to incredible scales. Some physicists propose that this inflation didn't just happen once, but continues eternally in different regions of space, giving rise to new universes all the time. These bubble universes could pop into existence, each with its own Big Bang, creating a vast and ever-growing multiverse. But how does this help us understand what came before our Big Bang? If our universe is just one bubble in a cosmic foam of universes, then the conditions that led to our Big Bang might have been shaped by events in other universes or even by the interactions between them. For example, collisions between bubble universes could have triggered the expansion we observe in our own. This idea suggests that the origins of our universe might be deeply connected to the broader multiverse, offering a new way to think about the question of what came before. Of course, the multiverse theory isn't without its challenges. One of the biggest hurdles is the lack of direct evidence. Since other universes, by definition, exist beyond our observable universe, we can't see or measure them directly. This makes it difficult to test the theory or confirm its predictions. However, some scientists are exploring indirect ways to look for signs of a multiverse, such as searching for imprints of collisions between universes in the cosmic microwave background, or studying the fine-tuning of physical constants, which some argue could be explained by the existence of multiple universes with different laws of physics. Despite these challenges, the multiverse theory has captured the imagination of both scientists and the public because it offers a radical new perspective on the nature of reality. It suggests that our universe might be just one small part of a much grander cosmic tapestry, where the rules we take for granted could be entirely different elsewhere. As we continue to explore this idea, we're not only pushing the boundaries of science but also redefining what it means to ask, what came before the Big Bang? Next, we'll dive deeper into the different types of multiverses proposed by scientists and how they might shed light on the conditions before our universe began. Now, let's take a closer look at the different types of multiverses scientists have proposed, each offering a unique lens through which we can explore the question of what came before the Big Bang. These models not only expand our understanding of the cosmos, but also challenge us to rethink the very nature of existence. First, there's the idea of bubble universes, which we touched on earlier. In this model, our universe is like one bubble in a vast cosmic foam, where each bubble represents a separate universe with its own distinct physical laws. These bubbles form as a result of eternal inflation, a process where space expands exponentially, creating pockets that eventually become self-contained universes. The fascinating part is that these bubble universes might collide or interact, potentially leaving traces in the cosmic microwave background. If such evidence were found, it could provide clues about the conditions that existed before our Big Bang, suggesting that our universe's birth was influenced by events in neighboring bubbles. Next, we have parallel universes, a concept that often captures the imagination. In this scenario, multiple universes exist alongside ours, each occupying the same space but separated by dimensions we can't perceive. These parallel universes could arise from quantum mechanics, where every possible outcome of a quantum event spawns a new universe. For example, if you flip a coin, one universe might exist where it lands on heads and another where it lands on tails. This branching of realities creates an infinite web of parallel universes, each with its own history and future. While this idea is speculative, it raises intriguing questions about whether the Big Bang was a singular event or part of a broader quantum process that generates countless universes simultaneously. Then there's the quantum multiverse, a concept rooted in the strange and counterintuitive world of quantum mechanics. In this model, every possible quantum state exists simultaneously, creating a vast array of universes that represent every possible configuration of particles and forces. Unlike bubble or parallel universes, the quantum multiverse suggests that all possible realities coexist in a single, interconnected framework. This idea challenges our understanding of time and causality, as it implies that the Big Bang might not have been a unique event, but rather one of countless possibilities playing out across the quantum landscape. Finally, some theories propose a mathematical multiverse, where every possible mathematical structure corresponds to a physical universe. In this view, the laws of physics aren't fixed but vary across different mathematical frameworks, creating a multiverse of infinite diversity. This idea pushes the boundaries of what we consider real, suggesting that the Big Bang might be just one mathematical solution among an infinite set of possibilities. Each of these multiverse models offers a different perspective on what might have existed before the Big Bang. Whether it's bubble universes colliding, parallel realities branching, quantum states coexisting, or mathematical structures defining existence, these theories challenge us to think beyond the limits of our observable universe. While they remain speculative, they provide a rich tapestry of ideas that could one day help us unravel the mysteries of our cosmic origins. Next, we'll explore how quantum gravity might hold the key to understanding the state of the universe before the Big Bang. Now, let's shift our focus to a groundbreaking idea that could revolutionize our understanding of the universe's origins: the quantum gravity hypothesis. This theory seeks to bridge two of the most profound frameworks in physics: quantum mechanics, which governs the behavior of the smallest particles, and general relativity, which describes the large-scale structure of spacetime. Together, they might hold the key to unlocking the mysteries of what existed before the Big Bang. Quantum gravity aims to reconcile the apparent contradictions between these two theories. While quantum mechanics deals with probabilities and uncertainties at the tiniest scales, general relativity paints a smooth, continuous picture of spacetime on cosmic scales. But when we try to apply these ideas to the extreme conditions of the early universe, they clash. This is where quantum gravity steps in, offering a potential framework to describe the universe's earliest moments or even what came before. One of the most exciting possibilities is that quantum gravity could reveal a pre-Big Bang state. Instead of a singular, infinitely dense point marking the beginning of everything, quantum gravity suggests that the Big Bang might have been a transition from a previous state of the universe. This idea challenges the traditional notion of a beginning and opens the door to a deeper understanding of the cosmos. For instance, some theories propose that the universe underwent a quantum fluctuation, a random event at the smallest scales which triggered the expansion we now call the Big Bang. Others suggest that spacetime itself might have emerged from a more fundamental quantum structure, hinting at a reality that existed before time as we know it. What makes quantum gravity so compelling is its potential to describe conditions where classical physics breaks down. Near the Big Bang, the density and energy of the universe were so extreme that the rules of general relativity no longer apply. Quantum gravity could provide the tools to explore these uncharted territories, offering insights into how spacetime and matter behaved in the moments, or even eons before the Big Bang. This could include scenarios where the universe was in a state of quantum foam, a chaotic, fluctuating sea of spacetime at the smallest scales, or where it existed in a timeless, pre-geometric phase. While quantum gravity remains a work in progress, its implications are profound. It not only challenges our understanding of the Big Bang, but also redefines what we mean by before. Instead of a linear timeline leading up to a singular event, quantum gravity suggests a more complex, interconnected reality where time itself might emerge from deeper principles. As we continue to explore this hypothesis, we may uncover clues that reshape our understanding of the universe's origins and its ultimate nature. Next, we'll dive into one of the most promising approaches to quantum gravity, loop quantum cosmology, and how it envisions the Big Bang as part of a cosmic cycle. Now, let's take a closer look at one of the most fascinating ideas within quantum gravity, loop quantum cosmology. This approach builds on the principles of loop quantum gravity, a theory that attempts to describe the fabric of spacetime as a network of tiny, interconnected loops. Unlike the smooth, continuous spacetime we're familiar with, loop quantum cosmology suggests that spacetime is fundamentally granular, made up of discrete units at the smallest scales. This granularity could have profound implications for our understanding of the Big Bang and what might have come before it. One of the key insights of loop quantum cosmology is that it avoids the singularity problem. In traditional Big Bang models, the universe is thought to have started from an infinitely dense and hot point, where the laws of physics as we know them break down. But loop quantum cosmology proposes a different scenario. Instead of a singularity, the Big Bang could have been a big bounce. This means that our universe might not have begun from nothing, but instead emerged from the collapse of a previous universe. Imagine a cosmic cycle where universes expand, contract, and then bounce back into a new phase of expansion. This idea challenges the notion of a definitive beginning and instead paints a picture of an eternal, oscillating cosmos. So, how does this work? In loop quantum cosmology, the universe's expansion is governed by quantum effects that become significant at extremely high densities. As the previous universe contracts, these quantum effects create a repulsive force that prevents the universe from collapsing into a singularity. Instead, it rebounds, leading to the birth of a new universe, our Big Bang. This bounce isn't just a speculative idea. It's supported by mathematical models that show how quantum corrections to Einstein's equations can smooth out the singularity, replacing it with a transition from contraction to expansion. What's particularly exciting about this theory is that it offers testable predictions. For instance, loop quantum cosmology suggests that some remnants of the pre-Big Bang universe might still be detectable in the cosmic microwave background radiation, the faint afterglow of the Big Bang. If scientists can find evidence of these imprints, it would provide strong support for the idea of a big bounce and revolutionize our understanding of the universe's origins. Loop quantum cosmology also raises intriguing questions about the nature of time. In this framework, time doesn't simply begin at the Big Bang. Instead, it transforms. The before and after of the bounce are connected in a way that challenges our classical notions of cause and effect. This opens up the possibility that the universe's history is far more complex and interconnected than we ever imagined. As we continue to explore loop quantum cosmology, we're not just uncovering new details about the Big Bang, we're redefining what it means to ask, what came before? The idea of a big bounce invites us to think of the universe as part of an endless cycle, where beginnings and endings are intertwined in a cosmic dance. Next, we'll explore another mind-bending theory, string theory, and its vision of the pre-Big Bang era. Now, let's shift our focus to another groundbreaking theory that takes us even deeper into the mysteries of the pre-Big Bang era, string theory. Unlike traditional physics, which describes particles as tiny points, string theory proposes that the fundamental building blocks of the universe are incredibly small, vibrating strings. These strings can oscillate in different ways, giving rise to the various particles and forces we observe. But what makes string theory truly fascinating is its suggestion that our universe operates within a framework of higher dimensions, far beyond the three spatial dimensions and one time dimension we experience. In string theory, the universe isn't just a four-dimensional construct. It could have as many as 10 or even 11 dimensions. These extra dimensions are thought to be compactified or curled up at such tiny scales that we can't detect them directly. However, they play a crucial role in shaping the behavior of strings and, by extension, the fabric of reality itself. This higher dimensional framework opens up entirely new possibilities for understanding what might have existed before the Big Bang. One of the key concepts in string theory is the idea of brains, short for membranes. These brains are multidimensional objects that can exist within the higher dimensional space predicted by the theory. Our universe, according to this idea, could be a three-dimensional brain floating within a higher dimensional bulk. This perspective changes how we think about the Big Bang. Instead of a singular event in an isolated universe, the Big Bang could have been the result of interactions between brains in this higher dimensional space. Imagine two brains colliding in this bulk. The energy released from such a collision could have sparked the expansion of our universe, effectively creating what we call the Big Bang. This scenario, known as the brain collision model, suggests that our universe's birth wasn't an isolated event but part of a larger, multidimensional drama. It also implies that other universes could exist on separate brains, each with its own unique properties and physical laws. String theory's implications for cosmology are profound. By introducing higher dimensions and brains, it provides a framework where the Big Bang isn't the absolute beginning but rather a transition point within a much larger cosmic landscape. This challenges the traditional notion of a singular origin and suggests that the universe's history might be far more complex than we've imagined. It also raises the possibility that the conditions before the Big Bang could be described and understood, at least in principle, within this higher dimensional framework. What's particularly exciting about string theory is its potential to unify all the fundamental forces of nature, including gravity, into a single coherent framework. This unification could help us answer some of the most pressing questions in cosmology, such as what triggered the Big Bang and what, if anything, existed before it. While string theory is still a work in progress, its mathematical elegance and conceptual richness make it one of the most promising avenues for exploring the deepest mysteries of the universe. As we continue to explore string theory, we're not just uncovering new details about the Big Bang, we're reimagining the very fabric of reality. Next, we'll dive deeper into one of the most intriguing models inspired by string theory, the ekpyrotic universe, which offers a compelling vision of the pre-Big Bang era. Building on the fascinating possibilities of string theory, let's now explore one of its most intriguing models, the ekpyrotic universe. This theory offers a bold and imaginative explanation for what might have happened before the Big Bang, rooted in the collision of brains in higher dimensional space. In the ekpyrotic model, our universe isn't the result of a singular explosion from nothingness, but rather the aftermath of a dramatic cosmic event. Picture two massive brains' multidimensional surfaces floating in a higher dimensional space. These brains, over time, move closer and closer until they eventually collide. The energy released from this collision is what we perceive as the Big Bang, the moment our universe began to expand and evolve. What's remarkable about this model is that it doesn't require a singularity, a point of infinite density, to explain the Big Bang. Instead, it suggests that the universe's birth was a transition, a phase change triggered by the interaction of these brains. This idea aligns with string theory's broader framework, where the Big Bang isn't an isolated event but part of a larger, multidimensional process. The ekpyrotic model also addresses some of the challenges faced by traditional Big Bang cosmology. For instance, it provides a natural explanation for the uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang. In this scenario, the collision between brains would have smoothed out any irregularities, creating the remarkably even distribution of energy we observe today. But the ekpyrotic model doesn't stop there. It also suggests that the universe's expansion wasn't a one-time event. Instead, it proposes that these brane collisions could happen repeatedly, leading to a cyclical pattern of universes being born, expanding, and eventually colliding again. This idea of a cyclical universe adds another layer of depth to our understanding of cosmic history, hinting that our universe might be just one chapter in an endless cosmic story. Of course, like any groundbreaking theory, the ekpyrotic model has its critics and unresolved questions. For example, how exactly do these branes move and collide? What governs their behavior in higher dimensional space? And can we ever find direct evidence of these collisions? While these questions remain open, the ekpyrotic model continues to inspire researchers, offering a compelling alternative to the traditional Big Bang narrative. As we reflect on this model, it's clear that string theory and its offshoots are reshaping our understanding of the universe's origins. The ekpyrotic universe challenges us to think beyond the confines of our four-dimensional experience and consider the possibility of a grander, multidimensional reality. Next, we'll turn our attention to another mind-bending concept, the holographic principle, which suggests that the universe's information might be encoded on a lower dimensional boundary, offering yet another perspective on what came before the Big Bang. Now, let's shift our focus to another groundbreaking idea that challenges our understanding of reality itself, the holographic principle. This concept suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface, much like a hologram. Imagine a movie projected onto a flat screen, but instead of just showing images, it contains the entire structure and complexity of the universe. This principle isn't just a wild idea, it's rooted in the mathematics of black holes and quantum gravity, offering a radical new way to think about the cosmos. The holographic principle emerged from the study of black holes, where scientists discovered that the information about everything that falls into a black hole isn't lost but is instead stored on its surface, known as the event horizon. This led to the idea that the universe itself might operate in a similar way, with all the information about space, time, and matter encoded on a lower dimensional boundary. In this view, our three-dimensional reality could be a projection of this two-dimensional surface, like a cosmic hologram. So, how does this relate to what came before the Big Bang? If the universe's information is encoded on a lower dimensional boundary, it's possible that this boundary existed before the Big Bang, serving as a kind of blueprint for the universe's creation. Instead of a singularity or a collision of branes, the Big Bang could have been the moment when this two-dimensional information was projected into the three-dimensional space we inhabit today. This idea flips our understanding of the universe's origins on its head, suggesting that the Big Bang wasn't the beginning of everything but rather the emergence of a new dimension from an existing framework. The holographic principle also offers a potential solution to one of the biggest puzzles in cosmology, the fine-tuning of the universe. Why does the universe have the precise conditions necessary for life? If the universe's information is encoded on a lower dimensional boundary, it's possible that these conditions were pre-programmed like a cosmic code before the Big Bang even occurred. This would mean that the laws of physics and the structure of the universe were set in place long before the moment of expansion we call the Big Bang. Of course, the holographic principle is still a theoretical framework, and many questions remain. How exactly does this encoding process work? Can we ever observe or test this two-dimensional boundary? And what does this mean for our understanding of time and space? While these questions are still being explored, the holographic principle has already opened up new avenues for research, inspiring scientists to rethink the very nature of reality. As we consider this mind-bending idea, it's clear that the holographic principle pushes the boundaries of our imagination, challenging us to see the universe not as a collection of objects in space, but as a vast, interconnected information system. Next, we'll delve deeper into how this principle could describe a pre-Big Bang state, exploring the idea of a holographic boundary encoding the universe's initial conditions. Building on the holographic principle, let's explore how this fascinating idea might help us understand what existed before the Big Bang. If the universe's information is encoded on a two-dimensional boundary, it's possible that this boundary predates the Big Bang itself. Think of it as a cosmic canvas where the blueprint for our universe was already sketched out before the moment of creation. This boundary could have contained the initial conditions, the laws of physics, the distribution of matter, and even the seeds of cosmic structures like galaxies, all encoded in a lower dimensional form. One way to visualize this is to imagine a movie script. The script contains all the dialogue, scenes, and directions, but it's only when the movie is produced that it comes to life in 3 dimensions. Similarly, the holographic boundary might have held the script for the universe, with the Big Bang acting as the moment when this script was brought to life, projecting the information into the 3-dimensional space we know today. This idea suggests that the Big Bang wasn't the absolute beginning, but rather a transformation from a lower dimensional framework into the universe we observe. This perspective also offers a potential explanation for the fine-tuning of the universe. If the initial conditions were encoded on the holographic boundary, they could have been carefully programmed to produce a universe capable of supporting life. This would mean that the precise balance of physical constants, the distribution of matter, and even the emergence of complexity were all part of the original design, embedded in the 2-dimensional surface long before the Big Bang occurred. But how could such a boundary exist without time or space as we know them? This is where the holographic principle gets even more intriguing. Some theories suggest that time itself might emerge from the encoding process, meaning that the boundary could exist in a timeless or pre-temporal state. In this view, the Big Bang wasn't just the beginning of space, but also the moment when time as we experience it began to flow. This challenges our conventional understanding of cause and effect, suggesting that the universe's origins might be far more abstract than we've ever imagined. Of course, this raises many questions. How does information transition from a 2-dimensional boundary to a 3-dimensional universe? Could we ever detect evidence of this boundary, or is it forever beyond our observational reach? While these questions remain unanswered, the holographic principle provides a compelling framework for rethinking the universe's origins. It invites us to consider that the Big Bang might not have been the ultimate beginning, but rather a pivotal moment in a much larger, more complex cosmic story. As we continue to explore these ideas, it's clear that the holographic principle challenges us to think beyond the limits of our 3-dimensional experience. It suggests that the universe's deepest secrets might be hidden not in the vastness of space, but in the intricate patterns of information encoded on a boundary we can't yet see. Next, we'll turn our attention to another groundbreaking theory that redefines the concept of before the Big Bang, the no-boundary proposal. Now, let's shift our focus to another groundbreaking idea that challenges our understanding of the universe's origins, the no-boundary proposal. Developed by Stephen Hawking and James Hartle, this theory offers a radical reimagining of what before the Big Bang could mean. Instead of a singular starting point, the no-boundary proposal suggests that the universe has no distinct beginning or boundary in time, at least not in the way we typically think of it. To grasp this concept, we need to step into the realm of imaginary time, a mathematical tool that helps physicists explore the universe's earliest moments. In this framework, time isn't a straight line with a clear start and end, but rather a curved, smooth surface. Imagine the universe as a sphere like the surface of the Earth. Just as the Earth has no edge or boundary, the universe in this model has no sharp beginning or end in imaginary time. Instead, it's a seamless, self-contained entity. This idea fundamentally redefines the concept of before the Big Bang. If the universe has no boundary, then asking what came before becomes a bit like asking what's north of the North Pole. The question itself might not make sense within this framework. Instead of a singular explosion from nothing, the no-boundary proposal paints a picture of a universe that smoothly transitions from a state of timelessness into the dynamic, expanding cosmos we observe today. One way to visualize this is to think of the Big Bang not as a starting point but as a kind of cosmic horizon. Just as the horizon on Earth isn't a physical boundary but a perspective we see from where we stand, the Big Bang could be a point beyond which our understanding of time and space breaks down. In this view, the universe doesn't begin in the traditional sense. It simply exists, with the Big Bang marking the moment when time as we know it starts to flow. This theory also has profound implications for the nature of existence. If the universe has no boundary, then the idea of a creator or an external cause becomes less necessary. The universe in this model is self-contained and self-explanatory, emerging from its own internal logic rather than an external force. It's a concept that aligns with the principles of quantum mechanics, where particles can appear and disappear without a clear cause, suggesting that the universe itself might operate under similar rules. Of course, the no-boundary proposal isn't without its challenges. Critics argue that it's difficult to test or observe, as it deals with conditions that are far beyond our current technological reach. Additionally, the concept of imaginary time, while mathematically elegant, is hard to reconcile with our everyday experience of time as a linear, flowing dimension. Yet, despite these hurdles, the no-boundary proposal remains one of the most compelling attempts to answer the question of what came before the Big Bang. As we reflect on this idea, it's clear that the no-boundary proposal invites us to think beyond the limits of our intuition. It challenges us to consider that the universe might not have a beginning in the way we imagine, but instead exists as a timeless, self-contained whole. Next, we'll explore the implications and criticisms of this fascinating theory, diving deeper into how it reshapes our understanding of the cosmos. Now, let's take a closer look at the implications and criticisms of the no-boundary proposal, a theory that continues to spark both fascination and debate. One of the most striking implications of this idea is how it reshapes our understanding of the universe's origin. By suggesting that the universe has no distinct beginning, the no-boundary proposal challenges the very notion of a starting point. Instead, it presents the cosmos as a self-contained entity, emerging from a state of timelessness into the dynamic reality we observe today. This perspective aligns with the principles of quantum mechanics, where events can occur without a clear cause, hinting that the universe itself might operate under similar rules. However, this radical reimagining of the universe's origins isn't without its critics. One major challenge is the difficulty of testing or observing the no-boundary proposal. Since it deals with conditions that are far beyond our current technological capabilities, it remains largely a theoretical construct. Critics argue that without empirical evidence, the theory is hard to validate, leaving it in the realm of mathematical elegance rather than observable science. Additionally, the concept of imaginary time, while useful for modeling the universe's earliest moments, is hard to reconcile with our everyday experience of time as a linear, flowing dimension. This disconnect raises questions about whether the no-boundary proposal truly reflects the nature of reality, or if it's simply a useful mathematical tool. Another point of contention is the philosophical implications of the no-boundary proposal. If the universe has no boundary or beginning, it challenges traditional ideas about causality and the need for a creator or external force. Some argue that this undermines the idea of a first cause, while others see it as a way to explain the universe's existence without invoking supernatural explanations. This debate highlights the tension between scientific theories and philosophical interpretations, showing how the no-boundary proposal pushes us to rethink not just the cosmos but also our place within it. Despite these criticisms, the no-boundary proposal remains a compelling framework for understanding the universe's origins. It invites us to think beyond the limits of our intuition and consider that the cosmos might not have a beginning in the way we imagine. Instead, it suggests a universe that exists as a timeless, self-contained whole, with the Big Bang marking the moment when time as we know it begins to flow. This idea, while challenging, offers a profound new way to approach the question of what came before the Big Bang. As we move forward, it's worth considering how this theory might evolve with future discoveries. Advances in quantum gravity, cosmology, and even technology could provide new insights or evidence to support or challenge the no-boundary proposal. For now, it stands as a bold and imaginative attempt to answer one of the most profound questions in science. How did it all begin? Next, we'll explore another fascinating theory that offers a different perspective on the universe's origins: eternal inflation. Now, let's shift our focus to a theory that paints a strikingly different picture of the universe's origins: eternal inflation. This idea suggests that the universe isn't just expanding, it's doing so endlessly with no sign of stopping. Imagine a cosmic balloon that keeps inflating forever, creating new regions of space faster than we can comprehend. This endless expansion isn't just a wild idea, it's a framework that could help us understand what might have existed before the Big Bang. At the heart of eternal inflation is the concept of a false vacuum, a state of space filled with energy that drives rapid expansion. Think of it like a pot of water on the verge of boiling. In some regions, the water bubbles and transitions to steam, representing the birth of new universes. In others, the water remains calm, continuing to expand. In this analogy, our universe is one of those bubbles born from a tiny fluctuation in the false vacuum. But here's the mind-blowing part: this process isn't a one-time event. It's happening endlessly, creating countless universes in an ever-expanding cosmic sea. This theory offers a fascinating explanation for what might have preceded the Big Bang. Instead of a singular, explosive beginning, eternal inflation suggests that our universe is just one of many, emerging from a larger, eternally inflating space. This means the Big Bang wasn't the absolute start of everything. It was more like a local event within a much grander cosmic landscape. It's a bit like discovering that your hometown is just one small part of an enormous, ever-growing country. But how does eternal inflation connect to the Big Bang? According to this model, the rapid expansion of space would have stretched tiny quantum fluctuations into the seeds of galaxies and cosmic structures we see today. In other words, the conditions that led to the Big Bang were shaped by the dynamics of eternal inflation. This idea not only redefines our understanding of the universe's origins, but also opens the door to a multiverse, a vast collection of universes, each with its own unique properties. Of course, eternal inflation isn't without its challenges. One major question is whether we can ever observe evidence of this endless expansion. Since the regions of space undergoing inflation are far beyond our observable universe, testing this theory directly is incredibly difficult. However, some scientists believe that subtle clues, like patterns in the cosmic microwave background or gravitational waves, might one day provide indirect evidence. Despite these challenges, eternal inflation remains a compelling and imaginative way to think about the universe's beginnings. It pushes us to consider that our Big Bang might not have been the first or the last cosmic event. Instead, it could be part of an infinite cycle of creation where universes are born, expand, and perhaps even collide, all within an eternally inflating cosmos. As we continue to explore this theory, it's worth reflecting on how it reshapes our understanding of time, space, and existence itself. Eternal inflation invites us to think beyond the boundaries of our universe and consider that the cosmos might be far more vast and complex than we ever imagined. Next, we'll dive deeper into one of the most intriguing aspects of this theory: the idea of bubble universes and how they fit into the grand tapestry of eternal inflation. Now let's zoom in on one of the most fascinating aspects of eternal inflation, the concept of bubble universes. Picture this: within the vast, eternally inflating cosmos, there are countless regions where the rapid expansion slows down, creating pockets of stability. These pockets are what we call bubble universes, and each one could be an entirely separate universe with its own unique set of physical laws and properties. It's like a cosmic foam where each bubble represents a universe floating in an endless sea of expanding space. In this model, our universe is just one of these bubbles. The Big Bang, then, wasn't the beginning of everything. It was the moment our bubble universe began to form. Imagine a pot of boiling water again. As the water bubbles and steams, each bubble that rises to the surface is like a new universe being born. Some bubbles might pop immediately, while others, like ours, stabilize and grow. This means that before our Big Bang, there was already a vast, inflating space filled with energy, and our universe emerged as a tiny fluctuation within it. But what's truly mind-blowing is that this process isn't limited to just one bubble. Eternal inflation suggests that new bubble universes are constantly forming, each with its own Big Bang. This means that our universe might be just one of an infinite number of universes, each with its own history, laws of physics, and even dimensions. Some bubbles might have more gravity, others less. Some might have stars and galaxies like ours, while others could be completely alien, with structures and phenomena we can't even imagine. This idea of bubble universes also helps explain why our universe appears so finely tuned for life. In an eternally inflating multiverse, every possible configuration of physical laws exists somewhere. It's like rolling a cosmic dice an infinite number of times. Eventually, you'll get a universe like ours where the conditions are just right for stars, planets, and life to form. In other words, our existence might not be a cosmic accident, but rather one of countless possibilities in an infinite multiverse. Of course, the idea of bubble universes raises some big questions. For one, how do these bubbles interact, if at all? Could they collide, creating cosmic fireworks on a scale we can't even comprehend? Some theories suggest that such collisions might leave behind observable traces, like ripples in the cosmic microwave background or gravitational waves. While we haven't found definitive evidence yet, the search for these clues is ongoing, and the implications could be revolutionary. Another challenge is understanding what lies outside these bubbles. If our universe is just one bubble in an eternally inflating sea, what does the rest of that sea look like? Is it filled with more bubbles, or is there something even more exotic beyond? These questions push the boundaries of our understanding, challenging us to think beyond the limits of our observable universe. Despite these mysteries, the concept of bubble universes offers a compelling way to think about the conditions before the Big Bang. It suggests that our universe is part of a much larger, more complex cosmic landscape, where the rules of time and space might be very different from what we experience. This idea not only reshapes our understanding of the universe's origins, but also opens up new possibilities for exploring the nature of reality itself. As we continue to explore these ideas, it's worth reflecting on how they challenge our perception of existence. Bubble universes invite us to consider that our universe might be just one small part of an infinite, ever-expanding multiverse where the possibilities are as vast as the cosmos itself. Next, we'll turn our attention to another groundbreaking theory, conformal cyclic cosmology, which offers a completely different perspective on the universe's origins and its ultimate fate. Now, let's shift our focus to a theory that turns the idea of a single Big Bang on its head, conformal cyclic cosmology. Proposed by the renowned physicist Roger Penrose, this theory suggests that the universe doesn't have a definitive beginning or end. Instead, it goes through an endless series of cycles, each one starting with a Big Bang and ending in a state that sets the stage for the next cycle. In this model, the Big Bang isn't the ultimate origin of everything, it's just one chapter in an infinite cosmic story. At the heart of conformal cyclic cosmology is the idea that the universe's expansion and eventual heat death don't mark the end of existence. Instead, as the universe grows colder and emptier, it reaches a state where all matter and energy are so spread out that time and distance lose their meaning. In this state, known as a conformal state, the universe essentially resets itself. The vast, empty expanse becomes indistinguishable from the conditions that preceded the Big Bang, allowing a new cycle to begin. It's like a cosmic phoenix rising from the ashes of its previous form to start anew. One of the most intriguing aspects of this theory is how it connects the end of one cycle to the beginning of the next. Penrose suggests that the universe's expansion and cooling don't just lead to a dead, empty void, they create the conditions for a new Big Bang. This means that what we think of as the Big Bang might not be a unique event, but rather a recurring phenomenon in an infinite sequence of universes. Each cycle could have its own unique history, with galaxies, stars, and even life forming and evolving, only to fade away and give rise to the next cycle. But how does this theory hold up against the evidence? Penrose points to patterns in the cosmic microwave background, the faint afterglow of the Big Bang, as potential clues. He and his colleagues have identified what they call Hawking points, which they believe could be remnants of black holes from previous cycles. These points, if confirmed, would provide a tantalizing glimpse into the universe's cyclical nature. However, this idea is still highly debated, and many scientists remain skeptical, calling for more evidence to support such a radical claim. What makes conformal cyclic cosmology so compelling is how it redefines our understanding of time and existence. Instead of a linear timeline with a clear beginning and end, the universe becomes an eternal loop where each cycle is both an end and a new beginning. This challenges us to rethink not just the origins of our universe, but also its ultimate fate. Could the universe we live in be just one link in an infinite chain of cosmic cycles? And if so, what does that mean for the nature of reality itself? As we explore these questions, it's worth considering how this theory fits into the broader landscape of cosmological ideas. While it offers a radically different perspective from models like eternal inflation or the multiverse, it shares a common thread: the idea that our universe is part of a much larger, more complex cosmic tapestry. Whether or not conformal cyclic cosmology proves to be correct, it pushes the boundaries of our imagination, inviting us to consider possibilities that go far beyond our everyday experience. Next, we'll dive deeper into the evidence and controversies surrounding this theory, examining the scientific debates it has sparked and the questions that remain unanswered. What clues might the universe hold about its cyclical nature, and how close are we to uncovering them? Let's find out. Now, let's take a closer look at the evidence and controversies surrounding conformal cyclic cosmology. Roger Penrose's theory hinges on the idea that traces of previous cosmic cycles might still be detectable in our universe today. One of the key pieces of evidence he points to is the presence of what he calls Hawking points in the cosmic microwave background, or CMB. These points are thought to be imprints left by supermassive black holes from earlier cycles, which evaporated over time due to a process known as Hawking radiation. According to Penrose, these points appear as faint, circular patterns in the CMB, serving as potential relics of a universe that existed before ours. The concept of Hawking points is fascinating, but it's also highly contentious. While Penrose and his collaborators argue that these patterns are statistically significant and align with predictions from conformal cyclic cosmology, many other scientists remain unconvinced. Critics point out that the patterns could simply be random fluctuations in the CMB, rather than evidence of a previous universe. The debate centers on whether these anomalies are truly meaningful or just cosmic noise. This uncertainty highlights the challenges of interpreting data from the early universe, where even small errors can lead to vastly different conclusions. Another point of contention is the mathematical framework behind conformal cyclic cosmology. Penrose's theory relies on a concept called conformal rescaling, which essentially allows the universe to reset itself by stretching and compressing space and time in a way that makes the end of one cycle indistinguishable from the beginning of the next. While this idea is mathematically elegant, some physicists argue that it may not fully account for the complexities of the universe's evolution. For example, questions remain about how structures like galaxies and black holes could transition seamlessly from one cycle to the next without violating known physical laws. Despite these challenges, conformal cyclic cosmology continues to spark lively debates within the scientific community. Its bold claims force us to reconsider fundamental assumptions about the nature of time, space, and the universe itself. Even if the theory isn't ultimately proven correct, it serves as a powerful reminder of how much we still have to learn about the cosmos. The search for evidence of previous cycles, whether through Hawking points or other means, pushes the boundaries of our observational capabilities and challenges us to develop new tools and techniques for exploring the universe's deepest mysteries. As we reflect on these debates, it's worth considering how they fit into the broader quest to understand the origins of our universe. Conformal cyclic cosmology offers a unique perspective, but it's just one of many competing ideas. Each theory, from the multiverse to quantum gravity, brings its own set of questions and possibilities. Together, they paint a picture of a universe that is far more complex and mysterious than we ever imagined. And as we continue to explore these ideas, we may find that the answers we seek lie not in a single theory, but in the interplay between them. Next, we'll turn our attention to another intriguing concept, the idea of a pre-Big Bang singularity. What does it mean for the universe to emerge from a single point of infinite density? And are there alternatives to this idea? Let's dive in and explore. Now, shifting our focus to one of the most enigmatic ideas in cosmology, let's explore the concept of the pre-Big Bang singularity. According to the traditional Big Bang model, the universe began as an infinitely dense and hot point, a singularity. This singularity is often described as a moment where all the matter, energy, space, and time we know today were compressed into an unimaginably small point. But what does this really mean for the state of the universe before the Big Bang? And why is the idea of a singularity so difficult to wrap our heads around? To understand the singularity, we need to think about what happens when we rewind the clock of the universe's expansion. As we go back in time, galaxies move closer together, temperatures rise, and the density of matter increases. Eventually, we reach a point where the laws of physics as we know them break down. At this stage, gravity becomes so intense that space and time themselves cease to behave in ways we can describe with our current understanding. This is the singularity, a point where our equations fail and our tools for making sense of the universe reach their limits. One of the biggest challenges in studying singularities is that they exist at the edge of our knowledge. General relativity, Einstein's theory of gravity, predicts the existence of singularities, but it doesn't tell us what happens within them. In fact, the equations of general relativity simply stop working at this point, leaving us with no way to describe the conditions inside. This has led some scientists to question whether singularities are real physical phenomena or simply mathematical artifacts, signs that our theories are incomplete. Another issue is that singularities defy our everyday understanding of space and time. In our normal experience, space is something we move through, and time is something that flows forward. But at a singularity, these concepts lose their meaning. Space becomes infinitely compressed, and time effectively stops. This makes it incredibly difficult to even imagine what before the Big Bang might look like. If time didn't exist in the way we understand it, can we even speak of a before at all? Despite these challenges, scientists have proposed several ideas to address the singularity problem. One approach is to look for a theory that combines general relativity with quantum mechanics, often referred to as quantum gravity. Such a theory might allow us to describe the conditions at the Big Bang without invoking a singularity. For example, some models suggest that quantum effects could prevent matter and energy from collapsing into an infinitely dense point, instead creating a quantum foam where space and time fluctuate wildly. Another possibility is that the singularity isn't the true beginning of the universe, but rather a transition from a previous state. This idea ties into theories like the Big Bounce, where the Big Bang was preceded by the collapse of a previous universe. In this scenario, the singularity marks a moment of transformation rather than an absolute starting point. While these ideas are still speculative, they offer intriguing alternatives to the traditional singularity model. The study of singularities isn't just about understanding the Big Bang. It's also about pushing the boundaries of our knowledge. By grappling with these extreme conditions, scientists are forced to rethink fundamental concepts like space, time, and the nature of reality itself. Even if we never fully understand what happened at the singularity, the journey to explore it has already led to groundbreaking discoveries and new ways of thinking about the universe. As we continue to probe the mysteries of the pre-Big Bang era, it's worth remembering that singularities are not just scientific puzzles, they are also philosophical challenges. They force us to confront the limits of human understanding and to ask questions that go beyond the realm of physics. What does it mean for something to have no beginning? Can we ever truly comprehend the origins of the universe? These are questions that may not have easy answers, but they inspire us to keep searching, keep questioning, and keep exploring the cosmos. Next, we'll examine some of the alternatives to the singularity model, exploring how other theories attempt to explain the universe's origins without relying on an infinitely dense starting point. Let's dive into these fascinating ideas and see how they reshape our understanding of the Big Bang. Now, let's turn our attention to some of the most compelling alternatives to the singularity model. While the idea of an infinitely dense starting point has long dominated discussions about the Big Bang, many scientists argue that singularities might not be the full story. Instead, they propose theories that avoid singularities altogether, offering fresh perspectives on what might have existed before the universe as we know it began. One such alternative is the concept of quantum fluctuations. In the quantum world, particles can pop in and out of existence seemingly out of nowhere. This strange behavior is a fundamental aspect of quantum mechanics, and some scientists believe it could hold the key to understanding the pre-Big Bang era. Instead of a singularity, they suggest that the universe might have emerged from a quantum fluctuation, a tiny, random event in the fabric of space-time. In this scenario, the Big Bang wasn't the beginning of everything, but rather the result of a quantum process that triggered the expansion of space and time. This idea shifts the focus from an infinitely dense point to a more dynamic and probabilistic origin, opening up new possibilities for understanding the universe's earliest moments. Another intriguing alternative is the idea of emergent spacetime. This theory suggests that space and time aren't fundamental aspects of the universe, but rather emerge from something deeper. Imagine spacetime as the surface of a pond, calm and smooth from a distance, but made up of countless tiny ripples when you look closely. In the same way, spacetime might arise from a more fundamental structure, such as a network of quantum particles or information. If this is true, then the Big Bang might not have been the beginning of spacetime itself, but rather the moment when spacetime as we know it emerged from this underlying framework. This perspective challenges the notion of a singularity by proposing that the universe's origins lie in a realm beyond our current understanding of space and time. Some theories even combine these ideas, suggesting that quantum fluctuations within an emergent spacetime framework could have set the stage for the Big Bang. For example, in loop quantum cosmology, a leading approach to quantum gravity, the universe undergoes a big bounce rather than a big bang. In this model, the universe cycles through periods of expansion and contraction, with each cycle avoiding a true singularity. Instead of collapsing into an infinitely dense point, the universe reaches a minimum size before bouncing back, driven by quantum effects. This not only eliminates the need for a singularity, but also suggests that our universe might be part of an endless cycle of cosmic rebirth. These alternatives to singularities don't just redefine the pre-Big Bang era, they also challenge our understanding of the universe's fundamental nature. By moving beyond the singularity model, scientists are exploring ideas that could revolutionize cosmology, from quantum origins to the emergence of spacetime itself. While these theories are still in their early stages, they offer exciting possibilities for understanding the universe's beginnings without relying on the limitations of singularities. As we continue to explore these ideas, it's clear that the search for alternatives to singularities is more than just a scientific endeavor. It's a journey into the unknown. By questioning the singularity model, we're not only rethinking the Big Bang but also pushing the boundaries of what we know about space, time, and the very fabric of reality. And as we'll see next, this exploration leads us to even more mind-bending theories about the universe's origins. Now, let's shift our focus to two of the most mysterious and dominant forces in the cosmos: dark energy and dark matter. Together, they make up about 95% of the universe's total content, yet we still know very little about them. But what if these enigmatic components played a crucial role in shaping the conditions before the Big Bang? Could they hold the key to understanding the universe's earliest moments? Dark matter, the invisible substance that makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it incredibly difficult to detect. Yet, its gravitational influence is undeniable. It holds galaxies together and shapes the large-scale structure of the cosmos. Some scientists speculate that dark matter might have existed in some form even before the Big Bang, potentially influencing the initial conditions that led to the universe's expansion. Imagine dark matter as a cosmic scaffold, providing the gravitational framework that allowed matter to clump together and form the first structures in the universe. Without it, the universe as we know it might never have taken shape. On the other hand, dark energy, which makes up about 68% of the universe, is even more mysterious. It's the force driving the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. But could dark energy have played a role in the pre-Big Bang era? Some theories suggest that dark energy might have been present in a different form, influencing the dynamics of the early universe. For instance, in certain cyclic models, dark energy could have been responsible for triggering the transition from a contracting phase to an expanding one, effectively setting the stage for the Big Bang. This idea ties dark energy not just to the universe's current expansion, but also to its very origins. Interestingly, some models propose that dark energy and dark matter might be interconnected, with one influencing the behavior of the other. For example, in theories where dark energy evolves over time, its interaction with dark matter could have shaped the early universe's density and structure. This interplay might have created the precise conditions needed for the Big Bang to occur, leading to the universe we observe today. While these ideas are still speculative, they highlight the potential importance of dark energy and dark matter in understanding the universe's beginnings. As we explore these possibilities, it's clear that dark energy and dark matter aren't just passive components of the cosmos. They might have been active players in the events that led to the Big Bang. By studying their properties and interactions, scientists hope to uncover clues about the universe's earliest moments and the forces that shaped its evolution. And as we'll see next, this exploration takes us even deeper into the mysteries of the pre-Big Bang era, where new theories and discoveries await. Now, let's take a closer look at how dark energy and dark matter might have shaped the universe even before the Big Bang. One intriguing scenario comes from cyclic models, which suggest that the universe undergoes endless cycles of expansion and contraction. In these models, dark energy could have played a pivotal role in transitioning the universe from a collapsing phase to an expanding one. Imagine dark energy as a cosmic reset button, pushing the universe to rebound and set the stage for a new Big Bang. This idea not only ties dark energy to the universe's current expansion, but also positions it as a key player in the very fabric of cosmic rebirth. Similarly, dark matter might have been instrumental in these pre-Big Bang conditions. In some theories, dark matter could have existed in a primordial form, providing the gravitational scaffolding needed to stabilize the early universe. Without its influence, the universe might not have had the necessary structure to transition smoothly into the expansion we observe today. Think of dark matter as the unseen architect, quietly shaping the cosmos long before the first stars or galaxies ever formed. Another fascinating angle comes from multiverse models, where our universe is just one of many. In these scenarios, dark energy and dark matter could have interacted in ways that influenced the birth of our specific universe. For instance, fluctuations in dark energy might have determined the initial density and temperature of our universe, while dark matter could have dictated how matter clumped together in the early moments. This interplay between the two forces might explain why our universe has the precise conditions needed for galaxies, stars, and ultimately, life to emerge. Some scientists even speculate that dark energy and dark matter could be two sides of the same cosmic coin, with their interactions driving the dynamics of the pre-Big Bang era. In certain theories, dark energy might evolve over time, altering its influence on dark matter and vice versa. This evolving relationship could have created the delicate balance required for the Big Bang to occur, setting the universe on its current trajectory. While these ideas remain speculative, they open up exciting possibilities for understanding the universe's origins. By exploring how dark energy and dark matter might have operated before the Big Bang, scientists are piecing together a more complete picture of the cosmos. And as we'll see next, this journey takes us even further into the realm of theoretical physics, where groundbreaking ideas continue to challenge our understanding of existence itself. Now, let's step into the realm of philosophy, where we grapple with one of the most profound questions of all. What does before even mean when we talk about the Big Bang? To understand this, we need to challenge our everyday notions of time. In our daily lives, time feels linear, a steady flow from past to present to future. But when we consider the Big Bang, we're dealing with a moment that marks the beginning of time itself. So, can we really speak of a before if time didn't exist yet? This question pushes us to rethink the very nature of existence. If time began with the Big Bang, then the concept of before becomes a paradox. It's like asking what's north of the North Pole. There's no meaningful answer because the framework we're using breaks down. Philosophers and scientists alike have wrestled with this idea, suggesting that our language and intuition about time might not apply to the universe's earliest moments. Some thinkers propose that time, as we know it, is an emergent property, something that arises from the structure of the universe rather than being a fundamental feature. In this view, the Big Bang isn't just the start of the universe, it's the start of time itself. This means that asking what came before might be like asking what's outside the universe. It's a question that doesn't fit within the framework of our current understanding. But this doesn't mean the question is meaningless. In fact, it opens the door to fascinating possibilities. For instance, some theories suggest that time could have a different nature at the quantum level, where cause and effect might not follow the rules we're used to. Others propose that time could be cyclical or even multidimensional, offering new ways to think about the universe's origins. These ideas challenge us to expand our thinking beyond the limits of our everyday experience. Ultimately, the question of before the Big Bang forces us to confront the limits of human understanding. It reminds us that the universe is far stranger and more complex than we can imagine. And as we continue to explore these ideas, we're not just learning about the cosmos, we're also learning about ourselves and how we make sense of the world. Next, we'll dive deeper into the philosophical implications of time and causality, exploring how these concepts shape our understanding of the universe's origins. Now, let's take a closer look at how time and causality intertwine with the mystery of the Big Bang. Causality, the idea that every event has a cause, is a cornerstone of how we understand the world. We're used to thinking in terms of cause and effect, a domino falling because it was pushed, or a plant growing because it was watered. But when we apply this logic to the Big Bang, things get complicated. If the Big Bang marks the beginning of time, then what caused it? Can there even be a cause without time? This is where our everyday understanding of causality starts to unravel. In the absence of time, the very idea of a cause becomes slippery. Some theories suggest that causality might not operate the same way at the universe's earliest moments. For example, in the quantum realm, particles can appear and disappear without a clear cause, governed by probabilities rather than strict cause and effect relationships. This raises the possibility that the Big Bang itself could have emerged from a quantum fluctuation, a random event in a timeless void. But if causality breaks down at the Big Bang, how do we make sense of the universe's origins? One approach is to rethink causality itself. Instead of seeing it as a linear chain of events, we might need to consider it as a more complex, interconnected web. In this view, the Big Bang isn't the result of a single cause, but rather the outcome of a network of interactions that transcend our usual notions of time and space. This shift in perspective challenges us to expand our understanding of how the universe works. It suggests that the rules we take for granted, like cause and effect, might only apply within the framework of our observable universe. Beyond that, in the realm of the Big Bang and what might have preceded it, these rules could be entirely different. This doesn't mean causality is irrelevant, it just means we need to think bigger. Philosophers and scientists have proposed various ways to reconcile these ideas. Some suggest that causality might be an emergent property, much like time, arising from the structure of the universe rather than being a fundamental feature. Others explore the idea of retrocausality, where effects can precede causes, flipping our understanding of time on its head. These ideas might sound strange, but they offer new ways to think about the universe's beginnings. Ultimately, the relationship between time and causality forces us to confront the limits of our knowledge. It reminds us that the universe operates on scales and in ways that defy our everyday experience. As we continue to explore these concepts, we're not just unraveling the mysteries of the cosmos, we're also redefining what it means to understand something. Next, we'll explore how advanced mathematics provides the tools to model these mind-bending ideas, offering new insights into what might have come before the Big Bang. Now, let's shift our focus to the role of mathematics in unraveling the mysteries of what came before the Big Bang. Mathematics, often called the language of the universe, provides the tools to explore ideas that are far beyond our everyday experience. When it comes to understanding the pre-Big Bang era, advanced mathematical concepts like topology and differential geometry become essential. These fields allow scientists to model scenarios that defy our conventional understanding of time, space, and causality. Topology, for instance, studies the properties of space that remain unchanged even when it's stretched or twisted. Imagine a rubber sheet that can be bent or folded but still retains its fundamental characteristics. This kind of thinking helps physicists explore the idea of a universe that might have existed before the Big Bang, one that could have been shaped in ways we can't yet fully imagine. By using topological models, researchers can investigate whether the universe's structure could have been fundamentally different in a pre-Big Bang state. Differential geometry, on the other hand, deals with the curvature and shape of spaces. It's the mathematical backbone of Einstein's theory of general relativity, which describes how gravity warps spacetime. When applied to pre-Big Bang theories, differential geometry helps scientists explore how the universe's geometry might have evolved. For example, it allows them to model scenarios where the Big Bang wasn't a singular starting point, but rather a transition from a previous state of the universe. This could mean that the universe we know emerged from a highly curved, compact space that expanded into what we see today. These mathematical tools don't just provide abstract frameworks, they offer concrete ways to test and refine theories. By using equations and models, scientists can make predictions about what the universe might have looked like before the Big Bang. For instance, some models suggest that the universe could have been a highly symmetrical, smooth space before the Big Bang, while others propose a chaotic, fluctuating environment. Mathematics helps us explore these possibilities, even if we can't yet observe them directly. But it's not just about creating models, it's about interpreting them. Mathematics allows us to translate complex, mind-bending ideas into something we can analyze and understand. It bridges the gap between the abstract and the tangible, giving us a way to grapple with questions that seem almost impossible to answer. Without these tools, our understanding of the pre-Big Bang era would remain purely speculative. As we continue to push the boundaries of our knowledge, mathematics will play a crucial role in shaping our understanding of the universe's origins. It's a reminder that even the most profound mysteries can be approached with logic, precision, and creativity. Next, we'll dive deeper into the challenges and breakthroughs that mathematicians and physicists face as they work to model these extraordinary pre-Big Bang scenarios. Now, let's take a closer look at the challenges and breakthroughs that mathematicians and physicists encounter as they attempt to model the elusive conditions before the Big Bang. While mathematics provides a powerful framework for exploring these mysteries, it's not without its hurdles. One of the biggest challenges lies in the fact that the pre-Big Bang era exists beyond the reach of our current observational tools. We can't directly observe what happened before the Big Bang, which means scientists must rely heavily on theoretical models and mathematical predictions. This lack of empirical data makes it difficult to test and validate these models, leaving many questions unanswered. Another major challenge is the complexity of the equations involved. Modeling the universe's behavior at such extreme scales requires solving equations that are incredibly intricate and often unsolvable with today's computational power. For example, quantum gravity, a theory that aims to unify quantum mechanics and general relativity, remains incomplete, and its equations are notoriously difficult to work with. Without a fully developed theory of quantum gravity, scientists struggle to describe the universe's behavior at the moment of the Big Bang, let alone what came before it. Despite these challenges, there have been significant breakthroughs that offer hope for unraveling these cosmic mysteries. One exciting development is the advancement of computational tools and algorithms. With the rise of supercomputers and quantum computing, researchers are now able to simulate complex scenarios that were once thought impossible. These simulations allow scientists to explore how the universe might have behaved under extreme conditions, providing valuable insights into potential pre-Big Bang states. Another breakthrough comes from the field of string theory, which proposes that the fundamental building blocks of the universe are tiny, vibrating strings. String theory introduces the idea of higher dimensions and brane objects that exist in these higher dimensional spaces. This framework has led to models like the ekpyrotic universe, which suggests that the Big Bang was the result of a collision between branes. While still speculative, these ideas offer a mathematically consistent way to think about what might have preceded the Big Bang. Additionally, the holographic principle has opened up new avenues for understanding the universe's origins. This principle suggests that all the information in a volume of space can be encoded on its boundary, much like a hologram. Some researchers believe this could provide a way to describe the universe's initial conditions without needing to understand the full complexity of its interior. This approach has the potential to simplify the mathematical challenges of modeling pre-Big Bang scenarios. As we continue to push the boundaries of mathematics and physics, these breakthroughs bring us closer to answering one of the most profound questions in science: what came before the Big Bang? While the journey is far from over, each discovery brings us a step closer to understanding the true nature of our universe's origins. Next, we'll explore how cutting-edge technologies and experiments are paving the way for even more groundbreaking insights into this cosmic mystery. Now, let's turn our attention to the future of pre-Big Bang research and the groundbreaking technologies that could revolutionize our understanding of the universe's origins. One of the most promising tools in this quest is the development of advanced gravitational wave detectors. These instruments, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have already transformed our ability to observe cosmic events by detecting ripples in space-time caused by massive objects like black holes and neutron stars. In the coming years, more sensitive detectors could potentially pick up faint signals from the earliest moments of the universe, offering clues about what might have existed before the Big Bang. Another exciting frontier lies in the realm of quantum computing. Unlike traditional computers, which struggle with the complexity of equations describing the universe's behavior at extreme scales, quantum computers operate on principles that could allow them to simulate these conditions with unprecedented accuracy. Researchers are already exploring how quantum algorithms might help solve problems in quantum gravity and string theory, bringing us closer to a unified understanding of the cosmos. While still in its early stages, this technology holds immense potential for unlocking the secrets of the pre-Big Bang era. In addition to these technological advancements, experiments in particle physics are also playing a crucial role. The Large Hadron Collider, for example, has already provided insights into the fundamental particles and forces that shape our universe. Future upgrades and new colliders could probe even higher energies, potentially revealing phenomena that existed in the moments leading up to the Big Bang. These experiments might uncover new particles or interactions that could reshape our understanding of the universe's earliest stages. Space-based observatories are another key area of focus. Missions like the James Webb Space Telescope are designed to peer deeper into the cosmos than ever before, capturing light from the first galaxies and stars. By studying the cosmic microwave background, the faint afterglow of the Big Bang, scientists hope to find subtle patterns or anomalies that could hint at events preceding the universe's birth. These observations, combined with theoretical models, could provide a more complete picture of the pre-Big Bang era. As we look ahead, the collaboration between theory and experiment will be essential. By combining insights from mathematics, physics, and cutting-edge technology, researchers are building a toolkit to explore the universe's origins like never before. While many questions remain, the progress being made today brings us closer to answering one of the most profound mysteries of all: what came before the Big Bang? Next, we'll delve into what we hope to discover through these efforts and how they could reshape our understanding of existence itself. As we venture further into the mysteries of the pre-Big Bang era, the discoveries we hope to uncover could fundamentally alter our understanding of existence itself. One of the most tantalizing possibilities is the detection of entirely new particles or forces that existed in the universe's earliest moments. These particles, which may have played a role in shaping the cosmos, could provide clues about the conditions that led to the Big Bang. For instance, if experiments at facilities like the Large Hadron Collider or future particle accelerators reveal particles with properties unlike anything we've seen before, it could open up entirely new avenues of research into the universe's origins. Another groundbreaking discovery could come in the form of evidence for other universes. If the multiverse theory holds true, we might find subtle imprints in the cosmic microwave background or gravitational wave signals that hint at interactions between our universe and others. Such evidence would not only confirm the existence of a multiverse, but also provide insights into how our universe fits into a much larger cosmic framework. Imagine the implications. Our universe might just be one of countless others, each with its own unique laws of physics and history. Advancements in quantum computing could also lead to breakthroughs in simulating the conditions of the pre-Big Bang era. By modeling the behavior of space-time and matter at unimaginably small scales, quantum computers might help us uncover phenomena that are currently beyond our reach. These simulations could reveal how quantum fluctuations or other processes might have set the stage for the Big Bang, offering a glimpse into the universe's very first moments. Space-based observatories like the James Webb Space Telescope could play a pivotal role in uncovering the universe's earliest secrets. By studying the light from the first stars and galaxies, scientists hope to find patterns or anomalies that point to events preceding the Big Bang. For example, subtle variations in the cosmic microwave background might reveal traces of a previous cosmic cycle or the influence of dark energy and dark matter in the pre-Big Bang era. These observations could help us piece together a more complete picture of how our universe came to be. Ultimately, the discoveries we hope to make could redefine not just our understanding of the Big Bang, but the very nature of reality. From new particles to evidence of other universes, each breakthrough brings us closer to answering one of the most profound questions in science: what came before the Big Bang? As we continue to push the boundaries of technology and theory, the answers we seek may be closer than we think. Next, we'll wrap up our exploration by reflecting on how these mind-blowing theories challenge our understanding of existence and inspire us to keep searching for the truth. As we bring our journey through the cosmos to a close, it's clear that the question of what came before the Big Bang is more than just a scientific puzzle. It's a profound challenge to our understanding of reality itself. From the Cyclic Universe Theory to the multiverse, from quantum gravity to the holographic principle, each theory we've explored offers a unique lens through which to view the origins of existence. These ideas don't just push the boundaries of science, they invite us to rethink what we know about time, space, and the very fabric of the universe. The beauty of these theories lies not just in their complexity, but in their ability to inspire wonder. They remind us that the universe is far stranger and more mysterious than we could have ever imagined. Whether it's the idea of an endless cycle of cosmic rebirth, the possibility of countless parallel universes, or the notion that our reality might be encoded on a two-dimensional surface, these concepts stretch our minds and ignite our curiosity. But the search for answers is far from over. Every discovery, every breakthrough brings us closer to unraveling the secrets of the cosmos. And as we continue to explore, we're reminded that the journey itself is just as important as the destination. The pursuit of knowledge is what drives us forward, and it's what keeps us asking the big questions. So, what do you think? Which of these theories resonates with you the most? Do you believe the Big Bang was truly the beginning, or could there have been something before it? Let us know your thoughts in the comments below. We'd love to hear your perspective. And if you enjoyed this deep dive into the mysteries of the universe, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on our next cosmic adventure. Until then, keep looking up and keep wondering, because the universe has so much more to reveal.